All right, today we're putting on our detective hats. We're going to dive into a field called spatial epidemiology. It's a world where the biggest clue to solving a disease outbreak isn't who got sick or what they have, but where.
So let's get right into it. Why is location so absolutely critical? Well, it all kicks off with a really simple observation. You've probably wondered about this, right? It never seems random. There's a reason cases pop up in one part of town and not another. And honestly, answering that very question is pretty much the whole reason this field exists.
Okay, so here's the official definition. But think of it like this. It's all about connecting the dots. We're taking health data, things like infection rates or where people are going to the hospital, and we're literally pinning it to a specific spot on a map to see what patterns jump out. And this, right here, shows you just how powerful this approach is. It lets us separate a scary coincidence from an actual cause. A map might light up with a lot of cases, but spatial epidemiology gives us the tools to figure out, hey, is that because there's a real local risk, or is it just because a ton of people live there?
So, how do we actually do this? How do we get this data onto a map? Well, to solve our public health mystery, we need the right kind of clues. Let's take a look at the fundamental building blocks we're working with.
The most common type of data is called vector data, and it's made up of three really simple elements. Just think of them as the basic shapes you'd use if you were going to draw a map of your neighborhood. First up, you've got points. It's the simplest clue there is. A single dot on the map could be a patient's home, a clinic, or the exact location where an exposure happened. Super simple, super important.
Next, we've got lines. Lines connect those points and show us pathways or networks. It could be a river carrying pollutants, sure, but it could also be the highway system that's helping a virus spread, or even something as tiny as the flight path of a single mosquito carrying a disease.
And finally, polygons. These are just enclosed areas that define some kind of boundary. They are absolutely crucial for grouping data into regions that mean something, like a city district, a state, or a specific park.
Now, while vector data is all about those distinct shapes, there's another type called raster data. Instead of shapes, I want you to picture a continuous grid of cells, kind of like the pixels in a photograph. This is perfect for mapping things that don't have hard edges, like air pollution, temperature, or rainfall. You can't really draw a neat polygon around that, can you?
Okay, so putting all this data on a map sounds pretty easy, but there's a huge technical hurdle that every single person who makes a map has to figure out how to get over.
Just think about it for a second. The Earth is a sphere, right? But your screen or a piece of paper is flat. So how do you make that translation happen without stretching some countries and squishing others?
This is such a great way to think about it. You just can't do it. You can't flatten an orange peel perfectly. Some part of it is always going to rip or stretch out, and it's the exact same problem with maps.
The solution, or maybe I should say the workaround, is called map projection. It's basically a set of mathematical rules for how you're going to flatten that orange peel. And get this, there are hundreds of different projections, and every single one is a compromise. Some will preserve the size of countries, others will preserve their shape, but none can perfectly preserve everything.
Okay, so we've collected our data, we've wrestled it onto a flat map. Now the real detective work begins, analyzing the patterns. And it turns out there's one fundamental law that underpins almost all of it.
This is it, Tobler's first law of geography. It sounds kind of fancy, but it's an incredibly simple and profound idea. It just says that nearness matters. In health, that means you're much more likely to be affected by a sick neighbor or a local contaminated well than by something happening thousands of miles away. Now here's the crucial part. Tobler's law basically breaks a key assumption in a lot of traditional statistics, the idea that all your data points are independent. They're not. A case of the flu in one house makes a case in the house next door more likely. They're connected. And because of that, we need specialized tools that can handle these spatial relationships.
And one of the primary goals of using these special tools is to find hotspots. These are those bright red areas on a map that just grab your attention, places where there's a statistically significant cluster of cases that's unlikely to be due to random chance.
But here is the million-dollar question we have to ask every single time we see one. Does this red spot on the map mean there's a higher risk of getting sick there, or does it just show us where a lot of people live? Telling the difference between those two things is one of the most important jobs of a spatial epidemiologist.
So let's see how this all comes together in the real world. Using these methods to improve public health is an incredibly powerful idea, but
as you can probably guess, it's also filled with all sorts of practical challenges. For one, the data is rarely perfect. A simple geocoding error could place a patient's house in the middle of the ocean. Unreported cases can create a map that's dangerously misleading. And then you've got to protect patient privacy, all while dealing with data like some zip codes that can be so broad they're almost useless for a detailed analysis.
But when we get it right, when we manage to overcome all those hurdles, the impact is just enormous. We can move from just describing where outbreaks happened to actually predicting them. We can build maps that show which areas are at the highest risk for malaria, which lets health officials target their resources exactly where they're needed most.
And that really leaves us with a final thought, doesn't it? We're getting incredibly good at mapping the problem, at pinpointing where disease is with stunning precision. So the next frontier, the next big question, has to be, how do we start to map the solutions? How do we use these very same tools to identify where our interventions are working, where resources should go next, and how we can build a healthier world, one location at a time?